In this video, we're going to be discussing end behavior. Now, end behavior for a polynomial function is defined as a behavior of the graph of the function as x approaches either positive or negative infinity. So what that means is how is the function behaving? If this is my function in the middle, how is it behaving as we extend the graph all the way down to either positive or negative infinity? I said that in reverse order. So is it going up or is it going down drastically? That's the idea behind this. End behavior for each end consists of an x and a y description. The left end and the right end will each have a description. And behavior starts in the middle and works outwards and is focused on what's happening at the end. This can be easily confused with increasing and decreasing instead, which moves from left to right. This chart is a chart that kind of summarizes if you're looking at left and right and up and down, and I'll use kind of that idea as I go through the examples. There is a notation for the mathematical form that is important. This arrow for the actual way of representing end behavior is read as the word approaches or goes to. But with that said, let's go ahead and take a look at some examples. Okay, so we're going to describe the end behavior of this function. I find it easier whenever I'm doing end behavior, at least for the first time, just to talk about the words up, down, left, and right, and look at that. So when we're talking about end behavior of a function, we'll typically be looking at a left side and a right side. There are some weird exceptions, but right now we're going to deal with polynomials, or this is an absolute value function, which behaves a lot like polynomials in terms of end behavior. So we're going to keep it kind of simple here and not look at the ones that end, such as logarithms or square root functions, which we'll talk about and deal with later in the year. But for polynomials and also for absolute value functions, we're talking about the left being as we go all the way to the left. So if I were to start anywhere on this graph, I usually start just right there, and I start moving to the left. As I run off, what is my function doing? Is it going up, down, or does it level off at a certain number, which is more for exponential functions than what we have today? But you can see it goes down as we're going off the side of the graph. So the left side, I would say, goes down. Now, if I go to the right side, I'm going to start in the middle again and then move to the right. What is happening for this graph? Well, as I run off to the side, you can see that we're going in a downwards direction. So the right goes down as well. Now, normally the words aren't the end-all be-all, but we can see that the left side is going down and the right side is going down as well. This is the gist of end behavior, but we want to describe it mathematically. That is one of the big purposes of Algebra 2, to prepare for those higher level math courses. So going through to describe this algebraically, thinking about it, left side, well, left and right are x descriptors. So whenever I talk about the word left, whenever I go to change that to mathematical, that's always going to be x. Now, x is approaching. Well, what type of x values are on the left? Well, negative x values are on the left. So if we go to the leftmost extreme, we're essentially approaching negative infinity. Then for the other word, down, that corresponds to this left end behavior. Well, left is going down. The down description is the y description. As I said with the definition, each end behavior has both an x descriptor and a y descriptor. So this is the y descriptor part, down. So we'll say y approaches. Well, what type of y values are down? Well, negative y values are down. So once again, we approach negative infinity. So the first end behavior, the left end behavior, is as x approaches negative infinity, y approaches negative infinity. We're going to do the same thing with the right side now. Right is an x descriptor. So x approaches. Well, what type of x values are on the right? And you can see we have positive x values on the right. And the more extreme to the right we go, the more positive it is. So positive infinity. And then down. So y will approach. What type of y values are down? Well, negative y values. Down will always mean y approaches negative infinity. Right always means x approaches positive infinity. So here is the second end behavior. And that's it. I'm going to be describing the end behavior of the function graph below. And just like we did before, we're going to use that same sort of approach, looking at the left and the right ends. Doing that thing where it zooms in on me again. There we go. RIGHT. Okay, so when I go to do end behavior, pick any point on the graph. For the left end behavior, doesn't matter where I start. I usually just start on the y-axis. If I go to the left, you'll notice that first it goes down. But we don't care that it goes down at first. This is called end behavior. So what happens at the very end? As I continue to go to the left, you can see at the very end, it goes up. We don't care that it goes down slightly as I move from left to right. In the end, it goes up on the left side. If I do the same thing on the right, you can see at first it goes up a bit. However, at the very end, which is what we're concerned with, it goes down. And remember, end behavior, you start in the middle and work outwards. So those are the end behavior in kind of a simplified word description. Now let's turn that into mathematical. Once again, left is an x descriptor. And what type of x values are on the left? Well, negative x values. So x approaches negative infinity. And up is a y descriptor. So y will approach, well, what type of y values are up? Well, positive y values. So positive infinity. And then for the right side, x will approach positive infinity. I'm writing wrong thing. Positive infinity because positive x values are on the right. And then for down, y will approach, well, what type of y values are down? Negative y values. So negative infinity. So the end behavior are these two facts. And there we go. Okay, in this video, I'm going to just kind of demonstrate how the end behavior of a polynomial is affected by something. And you can explore this a little bit more in depth yourself. So I'm going to use a very simple polynomial as a quadratic. You can look at my top line. Let's see if I can find my little circle thing. So you can see the top line. We have ax squared plus bx plus c. That's a simple quadratic. We have a, b, and c here. We're going to see which coefficients affect the actual end behavior of the function. So you can see up here right now, both ends are pointing up. So I'm going to go ahead and move one of the sliders. We'll start with a and see if that changes anything. So a, oh, you can see that a changes it right there. It does change it at 0. We're going to ignore 0 because if it's 0, that means it's no longer a quadratic. So we're going to ignore that from now. But you can see that it changes based on whether it's positive or negative, the end behavior. So ignoring 0 because that means it's not actually a quadratic, because 0x squared is just no x squareds at all. So if we skip over everything but 0, you can see that it does change the end behavior. So let's reset it to 1. Let's see if any of the other coefficients affect the end behavior of this quadratic. So I'm going to move b here. B, you can see that as I move b, both ends are still pointing up. So that's not actually affecting the end behavior at all. So let's go ahead and put it back to 1. And for c, let's do the same thing. Just focus on, again, both ends, see if that changes. So you can see it goes up there, or down, but both ends are still pointing up. So end behavior is not affected by c. With this, we can determine that in a polynomial, or at least in a quadratic, the end behavior is affected by the leading coefficient. Okay? And that actually extends to all other polynomials, whether it's quadratic, cubic, exponential. It's affected by the leading coefficient. Let's go ahead and look at the other thing that affects it. And I can do some more complicated experiments and stuff and show you this as well. The other thing that actually affects end behavior is its degree, its highest powered term. So right now we have x to the g as the example. Currently, g is 1. So this is basically x to the first. With x to the first, you can see that one side points up and one side points down. And then if I increase it to x to the second, you can see that both sides point up. Increasing it to x to the third, you can see that one side points up, one side points down. If I increase it to x to the fourth, they both point up again. And same thing, one side up, one side down, both sides up. Don't go into the negative for this one because that means it's not a polynomial any longer, so we're only focusing on positives. But if you look at that, it changes as we go to every other exponent. One up, one down, both up. One up, one down, both up. One up, one down, both up. So in result, it corresponds that if it's an even exponent or even degree, then both sides point in the same direction. In this case, both up because we have a positive leading coefficient. And if it's an odd exponent, odd degree, then one side will point up, one side will point down. Depending on the complexity of the equation, something different might happen in the middle. For example, if I add a bunch of crazy things in the middle, like plus 3x to the third, that might not actually do anything, plus 2x squared minus 7x. You can see that a bunch of crazy things is happening in the middle. But that doesn't change. This is still a 7th degree polynomial because g is still 7. But this middle stuff does not have any effect on what the end behavior is. Whether we only had that first term, the left side was pointing down and the right side was pointing up, or whether we get this super complicated equation, we still have the left side pointing down and the right side pointing up. So no matter what other terms we have, only that first term, that highest powered term, actually affects the end behavior of a polynomial. So we're going to go and summarize that in a graph, if I can go to the right screen. So we're going to summarize this in a chart here real quick. So the degree of a polynomial, whether it's even or odd, is one of the determining factors for the end behavior. And then the leading coefficient is the other determining factor. But the leading coefficient, you want to look at whether it's positive or negative. Okay, and just for the 4 possibilities that are going to happen, 1, 2, 3, and 4. So if it is even, then both sides are going to point in the same direction. If it's a positive leading coefficient, then both sides point up. And then if it's a negative leading coefficient, both sides will point down, which makes sense because whenever we had the negative leading coefficient for quadratics, when we talked about that transformations in the last unit, it created a reflection. So if both sides point up whenever the leading coefficient is positive, it's going to be reflected when it's negative. And for odd degrees, the right side points up and the left side points down. And of course, when the leading coefficient is negative, that's going to reflect it. So the right side will then point down. If we can draw a nice arrow there. And the sorry, I said the wrong words. The right side will then point down. Left side will then point up. And there we have the summary of end behavior with a polynomial function. In this example, we're going to be describing the end behavior of a polynomial function, 5x to the third plus 6x minus 9. Now, we could do this by graphing it. However, we're going to actually do this by using properties of a polynomial function when it comes to end behavior. So when we're using properties, we want to focus on the term with the highest power because that term is what ultimately determines the end behavior of a polynomial. If the polynomial is written in standard form, then that term will be first. We need 2 things from this term. We need the degree. In this case, the degree is 3. And we also need the leading coefficient. I'm going to abbreviate there. So the leading coefficient here is 5. When we check out the degree, we want to see if that is even or odd, and the degree is odd here. And for the leading coefficient, we want to see if it's positive or negative, and 5 is positive. So if we use those two pieces of information, refer back to the property I had in the previous chart, we know that the degree is odd, so it's going to follow this side here. And the leading coefficient is positive, so it's going to follow this row, which means the graph that's going to be most similar to is this one right here. So if I go and sketch that, we know it's going to be going up on the right and down on the left. Now, as you get more used to doing this, you won't even need to sketch the graph, but it does help. We don't really care about what's going on in the middle. It doesn't matter for end behavior. And having this graph does help you when you're first starting it. It just reinforces what end behavior actually is. But on the left side, I know my left arrow points down, and my right arrow points up. Now just turn that to mathematical. So left is x approaches negative infinity, while down is y approaches, well, negative y values are down, so negative infinity. And then for the right end behavior, right is x approaching positive infinity, positive x values on the right, and up is y approaches positive infinity as well, because positive y values are up. Whew. Okay, in this video, we're going to describe the end behavior of the polynomial function f of x equals 4x squared minus 9x to the fourth plus x to the third. And again, we could do this by graphing, but we're going to focus on instead on using properties of polynomials. And for that, we need the leading coefficient in degree. So we're going to focus on that highest power term, which happens to be here. This one is not in standard form, so be very careful not just to look at the first term here. If it helps, you can write it in standard form. That does help some people. If it's written in standard form, it would be this with the highest exponent, highest exponent first. But it doesn't change which term you should be looking at. You should be looking at that term with the highest power, because that's what determines the end behavior of a polynomial. So if we're looking at this, we're going to need the degree and the leading coefficient. So the degree of this polynomial is 4. The highest exponent is 4, which is an even degree. So I know either both sides are going to point up or both sides are going to point down. And the leading coefficient is negative 9, which is negative. Since the leading coefficient is negative, and since the degree is even, I know that both sides are going to be pointing down. You can use that chart that we did a couple minutes ago to help, but the left side will point down, and the right side will also point down. Describe it mathematically, so x approaches negative infinity, while y approaches negative infinity as well. And then for the right side, x approaches positive infinity, positive x values on the right, and y approaches negative infinity because negative y values are down. And there we have it, the two end behaviors, the left side and the right side. Okay.